Okay. All right, it is my great pleasure to welcome Bob Chant today. So for those of you who don't know Bob's history, Bob is a SoMAS grad, though I guess it wasn't called SoMAS.
MSRC back then.
MSRC.
Marine Science Teacher.
So Bob did his PhD with Bob Wilson. So Bob Wilson is my academic grandfather, which is a fun little piece of history. And just a comment, this is a great crowd. Bob's going to talk about the effect of urbanization on estuaries and physics in estuaries. So for those of you in 509, it's going to be a really great lecture to synthesize material we've been looking at. All right, Bob, thanks. Oh, and for those of you online, if you have issues with the audio or have questions, I'm going to moderate the chat, so you can just put the questions there. Okay. Thanks.
All right, thank Jack. It's great to be here. I think it's probably loud. Okay, great to be here. I was very excited to come here 35 years ago, and I feel the same thing today. So good to be here. So I'm going to talk about, as Jack said, some of the changes that are occurring in our estuaries due to urbanization, and I'm also going to talk a little bit about climate change. That it's going to be sort of a back theme here too, because in some ways, our estuaries, one thing to remember, estuaries are making deeper and deeper, due to dredging, but also so in some ways, maybe some of the stuff we're seeing is deepening is sort of a view of what might happen to teaching at sea level rise. So just a quick outline of my talk. I'm going to first sort of lay out the basic fundamentals of estuarine physics I'm going to use to interpret. Okay.
Is that all right?
Yeah, that's fine.
It's too dark.
It was pretty dark.
Yeah, that's fine.
All right.
Oh, yeah, I'm sorry. Keep going. I know why it was too dark.
Okay. Right. Okay, so I'm going to start off with a quick review of estuarine physics stuff that I learned here. Maybe a little more in the last 30 years as well. As we sort of advanced the field. And you're going to use some of this physics to put in contact with some of the changes we've seen in circulation and stratification in estuaries, both with observations and modeling. And I might have a few moments to say something about Jamaica Bay and how we change that too. So the simplest thing you can say about an estuary is that those who have studied estuaries or worked with them all know we have a very strong two-layer circulation, where the ocean water, the dense ocean water is drawn into the estuary, and the simplest thing you can say is a classic Munson relationship. The transport of inflowing water is equal to the river discharge times the outflowing salinity divided by the salinity. So if you look at this, and I remember years ago when I first saw this, I was here, and you go, oh well, as delta S goes down, the exchange flow goes up. Right? So that's like the first thing you might think about estuary. So more mixing, more exchange, of course, the students. So and so this is like really low hanging fruit that Munson had done in 1800. Okay, and there's Munson right there. We're a good company. There's Madame Curie, Albert Einstein, and Munson. So he was, this is of the day. So again, here you might think that mixing is going to equal 16. So about 50 years later, Donald Pritchard, who was here, actually on my video also, Pritchard, and then later Hansen and Rattray developed this theory of estuarine circulation and said that so this is the estuarine exchange flow has QE, and it's according to this theory that the exchange flow is proportional to the depth Q times the horizontal salinity gradient. So that so as you move up and down the estuary, the salinity gradient divided by this term here, which makes. So this theory then, at least at first glance, looks like the exchange flow is inverse proportional. Everything goes up, the exchange flow goes down. It contrasts to the Munson theory. Although it's also depending on ds dx, right? And so there's some interplay between these two. We'll get that to that. This term here is something we call vertical eddy viscosity. It's basically the mixing of the water column, which is accomplished by tides. And so one can write a simple parameterization for the eddy viscosity. It's going to be proportional to the tidal current amplitude times the water column depth. And you put that in here, and you might conclude that the exchange flow therefore is proportional to depth squared divided by tidal current amplitude times the horizontal. All this pointing to the sensitivity of depth to this exchange. And again, these are really nice cartoons of it from this really nice review paper by Brook and Geyer. And so again, to sort of play it to introduce everybody to the picture on the physics of estuaries. For this exchange flow, which we've drawn here as these arrows. So this is ocean water coming in, and this saline water, pressure water going out the surface. And these lines are say line as a pigment line of constant salinity. You can see how these exchange flows are going to strain these isotopes over and stratify the water. Right? So it's pretty straightforward. It's drain over water column. So this exchange flow UE times the horizontal salinity gradient acts to stratify the water. Okay? Stratification is really important parameter in estuaries. Influences a lot of the physics and a lot of water quality. And so we're interested in things that control stratification. Of course, if this is the only thing happening, the estuary get more and more stratified, something's got to balance. And of course, what balances stratification, that tendency for exchange flow, stratification, what balances that is mixing. Okay. And so if we were to balance out with mixing, I don't worry about the math of all this, but the mixing, you can see that the mixing is going to the mixing is going to go with something like an eddy viscosity times a vertical salinity gradient. So anyway, we can use this to ultimately say that the top to bottom salinity difference is going to scale with the depth cube again times the horizontal salinity gradient squared and the tidal current velocity squared. So again saying the top to bottom salinity difference is very sensitive to depth and very sensitive to salinity gradient. Okay, and so as we change depth of this, we might expect both the exchange flow and the salinity gradient to change. So one last slide of the physics before we go into sort of an overview of it is that and so what I'm describing here is an exchange flow. So
Just give it a second.
yeah, okay, maybe I'll work from over here. So what I've defined here basically is a exchange flow, the A squared times the FTX, and a top to bottom salinity difference. Okay, which has this complicated form here. So this exchange flow is bringing salt water into the estuary and pressure water leaving. Right? So that's going to drive a net salt flux up the estuary. So that's going to make the estuary saltier and saltier and saltier. So we get fresh salt water going bottom, fresh water going at the top. The balance, we have to balance that somehow. Well, how we balance that is river flow. The river flow is just trying to flush the water out of it. Right? And so what we have here is this sort of simple balance where this exchange flow times the top to bottom salinity difference is balanced by this is the depth, this is the river flow velocity times the mean salinity. Anyway, you plug all this in, and what you find is a very paradoxical result. That the exchange flow is independent of mixing. Okay, because what happens, because the mixing affects the horizontal salinity gradient portion of the tidal current velocity, where the exchange flow is 1 over the tidal current velocity. They cancel out. And so you can see the exchange flow is independent of depth and independent of mixing. And also paradoxically, is this theory that the stratification has also been tended. Okay, and that's because, again, the stratification, you might say, is 1 over mixing squares. It's times mixing, but the x scales with the tidal current. So you plug in this for that cancels out, and we find stratification is independent of mixing. Okay. So we expect, so the theory, if you assume that this balance with exchange flow driving salt up estuary is balanced by an export of salt by the river flow, we expect the exchange flow to be independent of mixing, and we expect stratification mostly independent of depth, more importantly. And we expect to change the salinity gradient, the top to bottom salinity difference to decrease, the depth decrease. And finally, this is kind of important here, that this is the SDX, which one can say is equal to the ocean salinity divided by the length of intrusion, because this is SO, this is S of fresh water, which is 0. And so the SDX is SO over L. And from that, you can say this is how far salt should go up an estuary. And so as the depth increases, salt should go further upstream. As tidal currents decrease, salt go further upstream. That's dependent on river discharge. And so again, if you modify estuaries, go through dredging or sea level rise, we might expect some of these to change. You might expect salt to change, but according to this theory, that the exchange flow should not change the stratification. That's the theory, and just as you know, if you're a reader of JGR or write paper for JGR, you have to now add a plain language summary, and so
what is W?
with yeah. So I'd say so at first glance, exchange flow stratification both increase with depth and the horizontal salinity gradient, right? That was the first equation, that equation in Pritchard theory. However, we find that the salinity gradient weakens as depth increases. And so once this sensitivity included, the theory suggests that exchange flow is insensitive to channel depth and only channel width and river discharge. The theory also suggests stratification decreases as depth increases. The salt intrusion length is sensitive to channel width, depth, river discharge, and mixing. And just as a side note, which is not really a side note, we'll look at this in the end, is that all this above theory ignores the effect of tide, the ability to tide to drive the mean fault. Tide to alter that mean fault. But many of these systems, it can be a dominant salt flow mechanism, particularly when things become weakly stratified. Okay. All right, a quick note on tides. Because tides are another important ingredient to modify the channel. As we deepen estuaries, we expect the tides. In the simplest case, and this is from a nice chapter by Carl Friedrichs in a book by Arnaldo Valley Levinson, who was also a student when I was here, too, about Wilson. But in a short estuary, by a short estuary is where the length of the estuary is very short compared to the tidal rate. So these estuaries are tens of kilometers long. The simple idea is that we have a scanning wave here, and the tidal current is going to go, the tidal current amplitude is going to go with 1 over the depth. So as estuaries deepen, we expect tidal current to decrease. Long estuaries are more complicated. It's got a dependency with 1 over the square root of H, but it's also proportional to what the tidal current, what the tidal range is. Okay? So in these short estuaries, the tidal range is the same everywhere. So it's very short. If you look like in Europe Bay, for example, you see the tidal amplitude is the same everywhere. Whereas you look in number of different estuaries, like even the Hudson, you'll notice that there is some long channel structure to the tidal amplitude. And so things that can control the long channel structures of the tidal amplitude will also affect the currents. And again, the currents is very important for mixing, salt intrusion, stratification, and later things. So all these are really important for the physics of the estuary and the biogeochemistry. And so what controls the amplitude of the tide as far as tidal range is this tendency, you can imagine the tidal wave propagates up an estuary, bridges want to dampen it. But flow convergence, we would say many estuaries are kind of funnel shaped, and that kind of converges the energy. And so you have friction trying to decrease the tide, convergence trying to increase the tide. And many estuaries, in fact, Delaware Bay is kind of like this, although we kind of knocked it out of this with some engineering dredging. But you have situations where friction equals convergence. Sorry, call that right. In which case the tidal amplitude, as you move up estuary, is fairly constant. So many estuaries, you'll see that you have this estuary very wide, gets narrower, 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 but the tidal amplitude remains the same. And that happens. This is sort of like a geomorphological equilibrium. Because, if estuaries kind of want to evolve to be, it may take a long time, it depends on the settings. But there's a tendency for estuaries to want to be synchronous, and that synchronous means that the tidal amplitude is constant moving up estuary. Now, there are systems that are unlike that, where in a case like this, where convergence might dominate over dissipation. In that case, the tidal range will increase going up estuary, and of course, you can have the opposite, where the tidal range will decrease. In this case, where friction overcomes convergence. And so, as we deepen our estuaries, we're going to change the first stuff I talked about: the ground circulation, stratification. We also going to change tides. Okay? And both are deepening them through channel deepening for dredging. Here's like, as these bigger and bigger ships have come in through the centuries, we've taken a place like Newark Bay and gone from, sorry, there's no scale here, but this is like 5 to 10 meters deep, and this is now 18. Okay, so we've deepened this thing significantly, and this is not the top of here. We'll look at Delaware Bay. We've done the same thing over much greater distance. All right, so we expect some of the things I talked about to change in a system like this, because we've deepened this thing significantly. We've also changed the width too. Right? We modified the width through land reclamation and things like that. And of course, sea level. We expect sea level to increase in estuaries too due to sea level rise. And here's the recent 2019 thing from IPCC, and here are the projections for RPC 8.5 and RPC 2.6. Okay, so there's 2100, and so we're looking at somewhere between maybe half a meter to a meter rise in sea level at 2100. Is what they're saying. I don't know if anybody feels the next piece last week at a time by David Paul's Wells about we've kind of dwindled too long to get this, but maybe we won't be here. Hopefully, be somewhere. But you guys might find out. I mean, so okay. So that's the layout of the theory. Here's now I'm talking about some studies we've done through the last 5 or 10 years in these systems. Newark Bay, I'll talk about first, Delaware Bay, and then a quick jaunt to Jamaica Bay at the end. Because I know some people here from working Jamaica Bay. And so we're going to start in Newark Bay and the Passaic River. And so, as I had said before, Newark Bay has been deepened significantly, and through projects of my own and others, I've been able to compile a bunch of data sets. I may be old, but I didn't collect this 1830 data set. But there's some data from the 90s, and then also in 2001, 2002, that should say, and then 2008, 2009. And so over this time, the system is right. So this has given us an opportunity to see how this estuary may respond to channel deepening. And so I think the next figure shows that actually, yeah. And so this shows. Oh, I should just comment that the sea level data is from. I moved the dot. That dot should be there, and then we have some ADCPs throughout the system in all these different years. And so the ADCPs will give us current, and then the sea level, of course, will tell us how the tides have changed. So here was this. So this is time. This is like 1995 to 2013. There was some short-term ADCP warnings in Newark Bay till then called 2001, 2002, and then some more out here in 2008 to 2009. Now I didn't write a proposal saying I'll make these measurements, we're going to deepen the channel, and again, this was the Army Corps deepening this channel to make do for the next 5 years. And so this gives us an opportunity to say, how does that theory respond? Does it fit the theory? And the theory again said that the exchange flow should change. We both looked at salinity data here, and it said the salinity should stratification should decrease. Just as a comment, like I said, I did like 1830 data, when I did go to the National Archives, and you go down to National Archives, there's these old tide books that people sat in the marshes and made measurements, sea level in 15 minutes for like 2 months. And you wrote down the book and you get some undergrad digitized for you. People can make some of that. And then there's a guy out at Santa Barbara, Stephen Talker, that has done a lot of this. And he was in fact authoring some of the papers that we wrote because he had digitized, he had an army of undergrads digitizing this data set. So let's look at what happened when we deepened Newark Bay. And so what I show here is this is some ADCP data from 97, 98, when this thing was about 14 meters deep. Okay, I'll explain what it is in a second. This lower panel shows the currents when it was 18. Okay, so when it was like about 14 to 18 meters. So the upper panel shows the tidal current amplitude. So what you're seeing here is spring neap variability. Okay, so spring tides, we were up over 90 centimeters per second. Spring neap tides we're down like in the 60s, but the mean tidal current amplitude in the 90s in the Coconut Gulf was about 75 centimeters. Okay. The exchange flow, and this is basically the surface flow minus the mid-depth flow at the bottom. There was a difference of about 7.5. Okay. You shoot forward, you go back, 10 years later, after they deepened this thing down to 18 years, you can see the tidal currents have in fact dropped. The exchange flow has increased. Okay, so unlike what the theory suggested, this has shown the exchange flow has doubled. Whereas if the salt field was able to adjust, it would not have. So if we go, I'm going to show you the profile. So this is the mean profile. These are long run deployments. This 98 is like a year and a half of data, and this is about 10 months of data. This is the vertical profile in the shallower system. This is in the deeper system. This is inflowing at depth and outflowing at the surface. So looking at that, remember the Hanson-Rabbit Pritchard theory said it should go with H cubed times the SDX. But the theory, if you allow the SDX just to deeper conditions, it cancels out the H cubed. But in this case, because Newark Bay is short, it can't adjust. And so because it's a short estuary, this actually also later gets stronger, and thus exchange flow basically doubled as the depth increased by the cube root of 2. So that's that. And so it didn't do this. The exchange flow was not constant. It was not independent of depth, but in fact dependent of depth. What I show here is for the deeper case, this is the blue line is the exchange flow over the course of the mooring deployment, and then the red line is theory. And this is river discharge versus exchange flow. And you can see the exchange flow does go with river discharge in 1/3 power, but it does seem to be very dependent on depth. That work. As I said, there's some smattering of salinity data. It's not quite as clear, but I just want to bring you down to this last figure down here, which shows a horizontal salinity gradient, and this is 0 PSU per kilometer. It's 0.5 PSU per kilometer. The black dots are the deeper channel, and the red dots are the shallower channel. So what it's showing is that if you deepen the channel, right, not down. The theory says deepen the channel, salt field should extend further up estuary. Because this estuary is relatively short, it couldn't make it way up. It couldn't go any further upstream. Basically, the salinity gradient increased. So before I conclude Newark Bay, I just want to note that the tidal ranges. I noted that the tidal current amplitude is 1 over depth times the tidal range. And the tidal range shows some variability over time. And again, there's a lot of error bars on the old data set. But at least the mooring that I have are in this time here. And you can see there's very little change in the tidal range. And so the changes I see in tidal currents, which went from like 75 down to 15 to 65 centimeters per second, were related to basically 10% reduction associated with chant deepening, another 5% associated with when the measurement for wave. There's this 18-year lunar cycle, and so once I count the 99 measurements for a 400 lunar cycle, the more recent ones during the weekly lunar cycle, but that's only about 5%, and so the 15% is most of the reduction of deepening. So just to wrap up Newark Bay, is that the SDX went up, not down, and because the salt field could not adjust because of limited length space. Mixing probably decreased because stratification increases, because of increased horizontal salinity gradient, and also tidal currents decreased. So the mixing decreased. So all the physics works together. Basically, the deeper water, the weaker mixing, the elevated salinity gradient all work together to increase. And I'm just going to add that this is in contrast to right next door, where Dave Ralston had a paper came out later showing that the same flow is independent in Hudson. The reason is Hudson is very long, and the salt field is able to adjust upstream. So the deepened Hudson River, salt went further up estuary, and the exchange flow. So this goes with H1 over H cubed, and they cancel it. But in the short system, they don't. Because they Newark Bay, the exchange flow cranks up, and it probably flushes in the middle. And so again, if you look at the morphology of Newark Bay, you can see that they had first deepened it, but if you look closely, you can see this channel that feeds up into Newark here, 34 was quite deep. And then they stopped, and then they built Port Elizabeth and Port Newark, and they stopped measuring that thing, and it's still there. And I bring this up, and I'll show you more details of it later, is when people run models to look at how estuaries might change with sea level rise. If one doesn't include things like morphological evolution, because sea level may rise to meter for 100 years, but we'll see sediment, the sediment that move up that much. Some estuaries can keep up a sea level rise, some cannot, which is another story. But and so in the case of Passaic River, again, my moorings were here, the salt field was able to adjust up to here, but it couldn't get much further. And in fact, as this fills in more and more up here, the salt field can only adjust here, so the salinity gradient is decent. And the reason I'm just going to quick point out this rapid deposition in the Passaic is Passaic River is like I said, they deepened it up to Newark, actually further upstream than that. And then they built Port Elizabeth, and then they started making Agent Orange on Passaic. And they laid down all this PCB dioxin, and then rapidly filled in. So this layer of buried PCB dioxin that are kind of staying buried here. As I said, this is a highly industrialized river. In fact, Alexander Hamilton had a factory on it. Oh, not him, this guy, right? But that was for Jack. Jack's a big Hamilton fan. But and so I'm going to just skip this figure and go to this and say, and so if what I showed here is this is getting at the rapid deposition in this channel, and so. And so what I show here is, as I said, they deepened this channel in 1950 to this. And you can see in 1995, it was, so this is going across the channel from the north side to south side. And you can see how rapidly from 1950 to 2004, it accumulated about 3 centimeters, 3 meters of sediment. Okay, and so this is where it was in 1940 when they actually stopped dredging it, and this is where it is. This is where it is. This is where it was in 1845, 45. Okay, so you see, with about in less than like 50 years, it went from or 60 years, it went from 8 meters deep, 3 meters deep, back to where it initially was approximately. It sort of regained its sort of geomorphological equilibrium. So the point is how rapidly sediments can accumulate in estuaries. And so again, and you do see a lot of modeling studies where people don't want to raise sea level a meter and see how the salt field changes in the estuary. Do that with some skepticism. So another way to do this is with modeling. This is our second case in Delaware Bay, and so this is a Delaware Bay. You can see it goes from this long estuary, so like North Bay, longer estuary. And what we've done, not we've done, but collectively we've deepened Delaware Bay, and this is kind of remarkable. This whole reaches like almost 100 kilometers from the mouth up to Wilmington, Philadelphia, and all the way up to Trenton almost. We've deepened this thing by 6 meters. And so at first glance you might say, well, they only deepened a very small part of the cross section, but it turns out we'll find out that all the salt flux is happening in the cross section. So just deepening that middle piece there, the main channel has a really important consequence of salt flux. So anyway, so here's Delaware Bay, and what we did in this project was we ran the simulation in a modern bathymetry, and then we had the digitized bathymetry from 1848 that we ran the model of that. So unlike saying going future, when we really don't know what the bathymetry is going to look like because of morphological information, here we know what the bathymetry is going to be. And I should say this was a project I think for Summerfield who tragically passed away years ago, but that I was closer with. So anyway, excuse me. So I just want to add that one thing in Delaware Bay is in addition to this channel deepening that's going on to the morphology, there's also, which is happening worldwide, incredible amounts of loss of wetlands. The bay as sea level rises, or perhaps as dredging occurs, the estuaries widen. And so, in fact, when I was down at the National Archives, I came across this drawing from 1882 of the tide gauge in Delaware Bay that I told you about. The guys, the tide gauge, and they measurements are right in that little book, and they notice a latitude and longitude that location. And if you put that on a map today, you find that location about 200 meters off out of the bay. So since the 1880s, this lost about 200 meters. No, sorry, that's 2 kilometers. It's moving about 10 meters a year. Much of the bay is moving about a meter or 2, but this one particular location is moving about 10 meters a year. And it's amazing if you go on Google Earth and you can look at the history, you can see the. So as far as the deepening of Delaware Bay, these are the channel depths from 1848, where it was approximately 20 feet deep, and then they started deepening in the 1890s, and then down to 45, and they're actually deepening since then 55. And so you can see in Philadelphia, there's been a pretty substantial increase in tidal range. This bay is deepened. So here we're seeing an increase in the tidal range, and even more robustly is in the upper reaches of the estuary. This is from a grad student of mine, Fernando Correa. You can see the tidal amplitude. So this was data. I should go back. This is from a tide gauge data in Philadelphia, where we see this. You can see like there's these jumps in the tidal range over time. And then Fernando ran simulations of the bay with the 1880 bathymetry. And so this is what the tide looked like in the 1850s, and this is the tidal range today. And you can see in the upper reaches of the bay, the tidal range more than doubled. and this propagating a little faster, but this rapid rise in the tidal range is mostly occurring in the Philadelphia region where they did some major engineering in the basin where they widened the river, straightened it, got rid of some shoals. And so if you're up here upstream and you're worried about sea level rise, you should also worry about the bigger tidal range. The high tide is higher because of sea level rise, the high tide is higher than these. And if you look at the tidal current amplitude, and I'll get back to why this is important in the bay. So this is 1848, and this is 2014, and this is 1848. You can see tidal currents, in the upper portion of the bay between kilometer 120 and 160, we're down around 60 centimeters per second. Today they are up by 8 per second. And so this is the tidal current in the main channel. This is on the shoal. And so if you look, you can see there's a lot more lateral shear in the flow, right? Today there's almost 60 centimeters per second difference between the main channel currents and the flanks, where in the 1880s it was much smaller. And this is actually very important on salt fluxes, which I'll comment on next. Here it is. Yes, the next slide shows. And so I talked about exchange flow, how exchange flow drives salt flux effect. I also commented that tides themselves can drive a net salt flux. And and so first I want to make this comment here. This is from another student of mine, Maria Zabel, who had done some modeling in Delaware Bay. And what she looks at is the salt flux in the main channel versus the salt flux on the flanks. And you can see that the salt flux of the estuary is dominated by the main channel and not the flanks. Even though the flanks are much wider, the salt flux is dominated by the channel. And so even though the channel is a small area relative to the whole estuary, that keeping the channel itself big impact on salt. Even though it's only 20% of the area of the estuary, you make that part deeper, you really impact the salt flux. So that's one important component. The other thing is I had mentioned that there's all the salt flux that I talked about was exchange, salt flux of exchange, but the tide can also drive salt flux. And so this is the ratio of the salt flux of tides versus salt flux through both tides and exchange flow. And you can see that particularly in the upper reaches of the estuary, where the end of the salt field is, that almost all of the exchange flow, all the salt flux is driven by tidal processes. And what can enhance that is lateral shear. And we see that we deepen the channel, there's more lateral shear in the flow, and that allows more salt flux of estuary. And this is important for a lot of reasons, and in particular, the city of Philadelphia gets the drinking water from Delaware. And so if you look at no, I hit the wrong button, but here we go. I got it. All right, let's see that. Go. But my fingers are too fast. And so, as I commented, there's this a lot more. This is again tidal currents in the main channel, tidal currents on the flank. So this variation, this cross-channel variation, has a tendency to drive more salt flux to allow salt to go further up estuary. And as I said, this is really important for Philadelphia, because Philadelphia is right up here, and the city of Philadelphia gets their drinking water from the river. And nowadays, so what this shows here, this is the river discharge at Trenton, and this is the big drought in the 1960s. After the 1960s, they don't let the river flow go below this. At this point here, if there's like this summer, for example, when it's dry, really plants are dying in your yard, the water from the reservoirs in upstate New York were being discharged into the Delaware River. So they don't let the river flow at Trenton go below 85 cubic meters per second. It does, they reduce water. And so it seems paradoxical that during drought they put water into the release water from reservoirs, but these reservoirs are feeding New York. right? In fact, some of this water actually comes from New Jersey too. And so there is this, battle over freshwater in the upper Delaware. And, as sea level rises, if we deepen this channel more, the question is, how is that going to affect water supply? And particularly drinking water. So that's a story to think about in the future. Okay, I think I'll finish up in time here. So just another quick comment of, in these model results, you can see that this is the mean river discharge of the Delaware River over a year. This is moving upriver. You can see the salt field during mean river discharge during 1848. You can see today the mean river discharge. The salt field goes much further west. So not surprisingly, the salt field goes further up estuary, and of course the tidal currents are stronger. And so if you look at suspended sediment concentration, you have much higher sediment concentrations today than you did back then, according to the model, because of stronger tidal currents and it's moved further upstream because the ETM is following, the estuarine intervening maximum is following the salt field. And so by keeping this channel, we increase tidal currents, we move salt further up estuary, we move sediment further up estuary, and this probably has impact on morphology of the system. And again, if we look at what this is showing here is the stress at the bottom of the river from 1848. This is the bottom stress in this is 1848, and the lower blue line is the upper line is 2014. The lower blue line is 1848. So you see a lot more stress in the water column, and these regions of a lot more stress on the bottom today than it was then. You can see there's much higher suspended sediment concentration in the system. But in addition to higher sediment concentrations, we also see a change in where deposition patterns are. And in fact, in 1848, during times of when the river was shallower and the salt field and turbidity magma further downstream, this is the tons per kilometer of deposition in this simulation. So we tended to accumulate sediment around kilometer 60. Today, this has moved upstream to kilometer 80. So not surprising, we keep in the channel, the salt field moved further upstream, carry sediment with it, and now sediment being trapped further upstream than where it was back then. And that again may have some to do with this area of rapid deposition in rapid erosion on these marshes that when I said this location here, where we lost 2 kilometers shoreline in the last 100 years, and you can see the simulations showed a lot more mud in the runs then than today. Although I must say that this doesn't seem to be sediment starved based on some of the work for some fields done on the marshes. But there does seem to be less mud available to go into the system. So a quick commentary on sea level rise. I basically said all this already. Is that for long estuaries, we expect the salt intrusion length to go with h squared. We want to tidal current speed. But as I mentioned, that because there can be rapid morphological adjustment. I mean, you're talking about 100-year time scale for meteor rise at sea level. Some systems can accumulate a lot of sediment. So it gets down to sediment supply, whether or not sea level rise or not. Some will, some won't, but many of us feel that simulations that run that don't consider future morphological adjustment should be viewed with some skepticism for how estuaries respond to changes in sea level. So I got just 2 slides on Jamaica Bay. This is another sediment starved system. I'm just going to get at how things might change with climate here. So this has been well known to be a 7-star system. Maybe this is how you get papers in PNAS. You have things like destroys New York City. But it's well known to be 7 stars, and that paper by Kirk Cochran and Renfro. The system is star with sediment, and we had done some work in there looking at sediment supply with some other colleagues, Dave Walton and Ganju. Just one quick point is that we made all kinds of estimates of sediment transport into the system. Turns out tides dominate sediment transport processes. But if you look at, I had some moored acoustics, which is the red, and then Neil Ganju had some optics, which are the black. And you can see that I generally, after I calibrated it, sometimes we matched up, sometimes we don't. Typically, the optics show much more sediment transport. And when is that? During big waves. When the ocean, these are waves like 20 miles offshore the ocean. And so when the sediment, so the point is here that the optics tend to respond to finer sediment than the acoustics. And so as I said, the dominant transport mechanism was tides, bringing sands in during the tidal cycles, but during stormy events, when there was we think that some of the relic sediment from offshore just be suspended and transported in. So if you look over here, what I show here is the average sediment supply to Jamaica Bay as a function of wave height offshore. The black and the red are the acoustic and the optics, but the red being optics. And you can see as the wave height gets offshore, it's larger, the optics really dominate. So this is the distribution of wave height offshore. So most of the time the wave is here, but these larger sediment supply during stormy times result in about a 50% more increase in the sediment supply according to the optics and acoustics. And I think that's because stormy conditions offshore produce more sediment than water column offshore, and that's transported to the base of the process. So maybe you could say we have a stormy climate, maybe we'll supply these systems more sediment. So that's just sort of a speculative thing. So finally, I'm just going to end. Estuaries will have different response to change in depth depending on the length. During estuary, I expect the rainfall to increase, and increase flushing time. The change will increase, and now will increase flush, decrease flush, and flushing time decreases. I'm sorry. The change will increases, flushing time decreases. Tidal currents decrease, and we expect reduced sediment concentration because of reduced tidal currents. In long estuaries, the change will remain the same, but yet flushing time will be longer because now the estuary is longer because estuary. Tidal currents generally increase. This is increased sediment concentration. And finally, sediment depositional patterns will be strongly modified by changes in depth, and perhaps storminess, but I think details of that are idiosyncratic. With that, thank you.
Right, question for Bob. You want to moderate or something? All right, question for Bob.
Yeah, go ahead.
Oh, okay. Well, I have two questions.
Sure.
The first one is, they're gonna put that, they have proposed, and it's gonna need to be approved, I don't know, the barrier on the Big Bay. How do you anticipate that impacting the flow of sediment in that area?
Yeah, very good question. And I have to say that I don't know the details of the design as much. I know that, like, for example, there's been work done on looking at the barrier across the Hudson. And so some of the questions are, how much will it flow? So if in the back to your place, like Jamaica Bay, so currently right now, if you look at sediment flux of the bay, it's dominated by tidal feeding. It's more, you're stronger stresses on the flood tide, and these spend more detail on flood tide. So it's possible if it's going to reduce tidal current, that's expected to be less. That's the first. The other thing is tidal barriers to reduce tidal current speed. Stratification has been increased, salt field has been installed. So that's one concern in the Hudson, if they were to build a barrier that didn't have that reduce, not all barriers do this, but some barriers might reduce the tidal amplitude propagating into the system. That would reduce tidal mixing in the estuary, allowing salt to go from the estuary, possibly filling with this work on this reduce the fluxing. So there's a lot of trade-offs, and they're very specific to the details. A nice paper by Dave Walston where he did that with the Hudson River. I showed you.
Oh, yeah, could you explain optics and acoustics?
Okay, so well, acoustics is so the acoustics I'm using are acoustic Doppler current. So it's like I had 1200 kilohertz ABC frequency. Oh, okay, yeah. So it's sort of a standard physical oceanographic instrument that measures currents, but it also gets backscatter. So it sends beams down to the water column, and based on the backscatter and opposite, we get current speeds, but then we calibrate them to sediment. Right? So we take a bunch of sediment measurements in the water column, we calibrate the backscatter, and we make that these sediments come through. The optics are similar, except that they're more sensitive to it's sort of like, you can imagine you can have the same amount of water in the atmosphere. It can be big raindrops of falling, right? So the optics, the backscatter, like they have different responses, and the optics tend to respond to finer sediments than the frequency that I was. So I think in my acoustic case, I was primarily seeing sand, which was sort of like, most of the time on sand going in, it's a very sandy environment, but when there were waves on there are some mud deposits offshore. During wave events offshore, some of those finers may have been suspended. Some of are suspended in more fine and more common in the ocean during filming events. And my acoustic were not seeing them, but the optics was. And just as a comment, that the modeling that we did with that also showed that Dave also called in that paper. Some of his sediments from Hudson were escaping out of the shelf, temporarily stored up the shelf, resuspended. Yeah.
I'm wondering about the survival of channel flow, like if it's rocky or maybe what's the hold on fine sediments, can be define the equation.
Oh, absolutely, yeah. Sorry, I kind of glossed over that. When I said that the mixing is equal to the drag coefficient times tidal current speed, that drag coefficient is exactly would be modified by the roughness. And so, that could really vary by factor. So, 2, 3, 4.
So question about the diversion of water to keep the salinity out of the Philadelphia water supply. And that also happens in Hudson because I think Poughkeepsie uses the river water also. So how does New York and New Jersey and Delaware fight over who gets the different reservoirs that are being dumped into the river?
Yeah, first of all, I've been I can talk about this one, but there's the difference in Poughkeepsie. Poughkeepsie's taking water out of the Hudson.
Yeah, right.
And then it goes to Poughkeepsie and it gets discharged back into the sewer system. New York gets water out of these reservoirs that built Catskills,
Right.
that would normally flow into the Delaware.
But they don't go into they don't divert them into the Hudson.
No, they do. So the aqueducts from New York.
But I mean,
They go to the Hudson. They go to Manhattan.
they don't divert them into the Hudson.
No.
So Poughkeepsie just suffers.
Yeah, I haven't been there with us, right? But so there's something called in that when that happened down in the 60s, they established the Delaware River Basin. And the Delaware River Basin Commission is the one that manages New York, Philadelphia, New York, Pennsylvania, Delaware, all have assets from the control that river, and so it's there's something called the river master. The woman is the river master. He is the one that actually, I don't know if he's dial in her office, but they release, You know, and then if you go to, like this summer, I was looking at this, guys at moorings up there. And you can see when the river goes down below, 85 cubic meters per second, they don't like peg it at 85, they kind of boom, to the daily pulse of the river. That's releasing water from the reservoirs that would normally go to New York City, which is now going back. And just as a side note, there's something called the Delaware River, the Delaware Raritan Canal, which connects the Delaware River to the Raritan River where I live. And then there's a flow of water that comes down that canal into New Brunswick, initially for coal, but now it's a nice park and immediately water. So there's several, there's I don't know the exact numbers, but there's tens of cubic meters per second of water coming from the Delaware Basin to New York. And so this is interesting, you know, how this is going to play out. So, you know, there's Delaware Basin Commission that is ultimately responsible.
So it's not just the Arizona that's fighting over the water.
That's right, that's right, that's right. First, we're pretty wet here, but you know, this summer, you know, no, it was a dry summer, it was, yeah. Come in.
So let's go back to this independence of mixing.
Yeah, no,
I have trouble.
okay, yeah.
It seems it's based on the assumption that the SDX is linear. If it wasn't linear, that would not work.
Well, yeah, I mean, so the core assumption of DXDX, the silly rates are uniform. But again, you're basically, you know, as you increase mixing, the estuary gets shorter. Right, so this is like 10 PSU, and this is 20 PSU. And you increase mixing, the estuary gets shorter. That causes the exchange flow to increase. And now the exchange flow times the STX, which is now bigger, gives you more stratification. So that's how increased mixing ultimately results in no change. There's a nice paper by Robert Edwin that did my DLI simulation. But you know, when I was here working in the Hudson River, you know, spring tide was mixed, neap tide was stratified, and I said, oh, of course mixing is important, but it's not steady state. If you all those things are steady state, so if we, you know, during spring tide, it's already a mix. If you like keep spring tide for like 2 months, the salt fill will get pushed all the way downstream as the headlines get close together. That would increase the exchange flow, increase the strain. But you're right, DSDX is not uniform, it's not uniform depth, it's not uniform channel, that does complicate it. So then you get to like, you know, from Genesis and topologies. Yeah.
We care about the fresh ground.
You care about what?
Mixing the fresh ground. Like
From groundwater. I don't think so. On these systems, I'm gonna say not. I'm gonna say because I mean, if I look at if you go out and measure mixing with microstructure, you see rainy variability, you see flood head variability. And I just think, and then you see mixing changes by orders of magnitude over spring neap and flood ebb. And so I don't think that whatever groundwater we do. I mean, it could be some shallow lagoonal system with no weak tides, but I would say these systems. Yeah.
So, made a comment on this, I think, but one of the things we've heard about over the years, the removal of oyster reefs from the boundary regions is something necessary. But also they were removed throughout the entire salty reach of estuary where you get tidal flats that traditionally or historically before the mid-1800s had huge populations of oysters all along the shoreline, and they were removed. And I'm wondering about the drag coefficients, the drainage on the flat areas, the total alteration of that in the 1800s. How does that enter into your?
Yeah, absolutely. It's I thought about this for a while. I'm going to back up and say, initially, when we were looking at this shoreline erosion, this was the coastal sea project. We had to do Dave, Chris, and Rock Gunner, for something like Gunner. What really motivated that was this rapid we find a way to find it probably wasn't so much. But it would, because the waves are barely filling in the bottom of the bay, but tidal currents happen. You know, and so, your question about, you know, increasing the, you know, CD drag. Presumably that would make the salt field shorter. This is a side note, is that Rutgers has a long history of marine science going back to this guy, Nelson. And Nelson was came there to work at the ag at the land grant college to work in poultry, and realized that oysters were grown the same way as farming, and so he got into agriculture. He done over there, and then testified in front of the Supreme Court about the effect of salt water taken from New York on oyster population. So, and I have a student right now who's writing the last chapter trying to get that history figured out. They don't put it back. But yeah, absolutely. I think it's a very interesting question how oyster reefs influence hydrodynamic estuaries. You know, I've seen people run models with absurd amount of oyster reefs. They're way out. I told my oyster colleagues. There's no way to rare data support that. But there's no doubt increasing the evacuation on time. It's right there on the equations. Yeah.
Another biology question. You mentioned the strong effects on turbidity
Yeah.
over time.
Yeah.
And I know the Hudson is very strongly light limited.
Mhm.
It's mid-Hudson.
Yeah.
So over time, has anybody tried to model the primary productivity changes in Delaware? Will it go down as the sediment is moving upstream? And
Well, that's a good question. Yeah, I mean, you know, the Chant did some of this, but we never looked at like changes in depth. Yeah, I think it's you know, of course, you will know that they say the water clarity is still cleaner than the big ocean population. So they're pumping, you know, that provided kind of like, you know.
not further up, not further up in
Yeah,
the hill where they were the Hudson.
Okay, yeah.
They never not with their.
Yeah.
that sort of thing.
Yeah. But yeah, I suspect that, you know, that light follow that too. I don't know, maybe try to.
And are there any general knowledge in Delaware, are marine fisheries moving upstream over time as deepening has occurred?
Well, the thing that's been confounding that is that oxygen of these species are up, you know, and so now it's recovered a lot. In fact, you know, the Delaware Basin Commission just told the Philadelphia Water Department that they got to reduce my ammonia. They want sturgeon to get past. You know, right now, even though oxygen levels are much better than they were, it's still they think it's still influenced to sturgeon, and so they want to continue the oxygen levels goes up on there. It's smoke sturgeon.
All right, let's go ahead and thank Bob.
Maybe